Assalamualaikum and hi everyone. My name is Zurina Binti Shamsuddin, and for this week we will cover chapter 7, which is entitled Mechanical Properties of Metals and Alloys, part 1. So in this chapter, we want to study how actually the various mechanical properties are measured and what these properties, for example, stiffness, strength, ductility, and also the toughness represent. Okay, this is the outlines. The 7.1, we will cover introduction, what is actually the definitions of the mechanical properties. 7.2, the concept of stress and strain. 7.3, elastic and plastic deformation. And 7.4, stress strain diagram. Okay, so for the course learning outcome for the subject, yeah, it is have a 3, but for this chapter, we will cover under the LO2, which is to analyze the properties of the engineering materials based on its structure. So the learning outcomes to define the engineering stress and engineering strain, compute the stress and strain under the different types of loading. So in the processing, basically structure, the properties, the performance scheme, reasons for studying is the mechanical properties can be due to these all the problem statements. So this is a list of the problem statement, which is the reasons, why actually we need to able to calculate the stresses, which is very important because it allows us to predict when actually the object will fail. So we look for the first one, what are they and why are they used instead of the loads and also the deformations. So this is the reason why we need to know about the stress and also the strain. So is the object strong enough to withstand the loads that will be applied to it? Will it break or fracture? Will it continue to perform properly under the repeated loadings? Okay, so that's why we need to calculate the strength, the tensile properties. So will the object deflect or deform or much that it cannot perform its intended function? We will look under the stiffness, and when loads are small and how much actually the deformation occurs. What material deform the least? So elastic behavior, and what point does permanent deformation occurs, and what materials are more resistant to the permanent deformations. So we will look into the plastic behavior. And last but not least, will the object suddenly bend or buckle out of shape at some elevated loads so it cannot no longer continue to perform its function. So this is under the stability, right? So we move to the definition of the mechanical properties. So in this case, actually, if a load is a static, all right, so what actually will expected it will occur? So it actually reflects the relationship between its response or deformations to an applied load, and its behavior when subjected to the external load shows the elastic and plastic deformations before failure, and frequently expressed as a function of the stress and strains. Okay, we measured using various mechanical testing, which it can be under the tensile test, the impact test, the what they call the flexural test. Yeah, in order we want to identify the mechanical properties. It's also the response of the material to applied forces depends on the types, the nature of the bonds, and the structural arrangement of the atoms and molecules or ions. So basically, there are several of the factors that we need to consider. So the first one, the nature of the applied loads, yeah, the environmental, the condition, the duration, and also the temperature. So this is actually the material property assessment that we can actually do to the types of materials. So this is actually the properties, and this is actually the type of the assessment. So if we want to know the hardness of the material, we can use the micro or macro hardness test. And for the tensile properties, which is the strength, the ductility, the elongation area of the reduction, or it can be from the yield strength to get the magnitude of the tensile strength, the modulus of the elasticity, the fracture strength, stiffness, and flexure strength. We can done under the tension test. And also, if you want to find the properties of the creep of the materials, you can use the creep test, the torsion, using the torsion test, the toughness, the impact test, and fracture toughness. Last but not least is the fatigue, which is you are using the SN fatigue test. Okay, so the concept of the stress and the strain. In this case, okay, if a load is actually static, yeah, or change relatively with the time, and is applied uniformly over the cross section or the surface of the member, okay, we can say that the mechanical behavior may be ascertained by a simple stress strain test, and this commonly conducted for the metal at room temperature. Okay, so a destructive test, for example, tensile test, that is the test specimen is permanently deformed and usually will end up fracture. Okay, there are four principal ways, yeah, in which a load may be applied, which is namely as a tensile, as a compressive, as a shear, and also a torsion. So this is actually an animation to show you how actually the member is changes, yeah, by the time that we impose the loading. Also that we can say that in this engineering practice, many loads actually for the torsion, yeah, is very frequently been applied compared to the shear as illustrated in the D, right? Okay, we move to the first part, yeah, which is the tensile stress and strain. Okay, in this part, there's several which is we will be touched, yeah, under the concept of stress and strain. Okay, one of the most common mechanical stress and strain test is performed in the tension. So when the metal is subjected to the two equal or opposite axial tensile loads denoted by the PT, T is actually a tension. Yeah, as you can see from this figure. Yeah, then the stress induced at any section of the metal which is known as the tensile stress. Okay, so there will be a decrease in the cross-sectional area and increase in the length of the metal. So for example, this is actually the metal before being pulled, and this is actually the metal after the pull. So we can see actually here is actually the uniformly the tensile stresses occurred. So the ratio of the increase in the length to the original length is known as a tensile strain, okay, which is the elongated one. Okay, so you can see the second figure show you the whole of the picture, the whole of the guide diagram, which is imposed by the tensile load. Yeah, it been elongated, and if you cut into the center, which is present into the second figure, it show you that the tensile stresses, yeah, is what they call developed, yeah, whereby that whatever that actually the external load be imposed to the member, the value that which actually feel by the member will be equally with the internal stresses over here. Okay, and we can also say that the output, yeah, the output from the tensile test can be represented, yeah, as a load and also as a elongation. Yeah, so a specimen deform usually to fracture with a gradually increasing the tensile load that is applied uniaxially along the long axis of the specimen. So the tensile testing machine is designed to elongate the specimen at a constant rate and to continuously and simultaneously measure the instantaneously applied load, yeah, with the load cell attached to the machine and the resulting elongation. In this case, we are using the extensometer. So in this case, the loads are normalized to the respective parameters of the engineering stress as well as the engineering design. Okay, the load deformation characteristics are dependent on the specimen size. So where that to compare the specimen of the different size, the load is calculated per unit area, which is denoted by the A0. So these definitions of the stress and strain allow one to compare the test results for the specimens of different cross-sectional area and different length denoted by the L node. Okay, so this is actually the schematic picture, which is we can see that here the size of the gauge length given as well as the area that might be experience the diameter being reduced after the force being applied in the tension direction. So this is actually the engineering stress. So we can actually define it. So the engineering stress, which is the sigma, symbol sigma, is defined according to the changes, the changes in the gauge length and the changes in the instantaneous load applied to the specimen divided by its cross-sectional area before any deformation occurred. Okay, so this is actually the common formula given, the sigma, which is the stress, equal to the force applied over the area, okay, which is noted as equation number 1. Okay, so the stress, engineering stress in the unit of megapascal, and the force is the load applied perpendicular to the specimen cross-sectional in the unit of Newton, and the area is actually original cross-sectional area in the meter square. So this is actually the formula that you need to memorize, which is a common formula for all of the tensile tests. So the unit can be in the Newton meter square in the unit SI. So how about the engineering strength? This engineering strength is defined according to the change in the gauge length, of the specimen divided by its original gauge length. So you can see it denoted by the epsilon. The what I call here, this is actually your engineering strength epsilon, and this is your original length, and this is actually your instantaneously length. Okay, then this is the changes of the length, which is denoted by the equations number 2. Alright, so for your information, the strain is always dimensional. Sometimes the quantity of the changes of the length is denoted as this symbol. Okay, we need to say that the Li minus the L naught can be denoted as the change, the symbol of the square here, triangle. So the engineering strain, we also can subsequently call as a strain, is unitless. So sometimes we can be expressed as in a percentage. Right, so now we move to the second part, which is the compressive stress and strain. So it's more similar, the concept with the tensile test. So the compression test basically, where the compression stress and strain test may be conducted if in the surface forces are of this type. Okay, so a compression test is conducted in a manner similar to the tensile test, except that the force is compressive, the compressive, towards the member, and the specimen contract along the direction of the stress. Okay, so the equations similar as tension are utilized to compute the compressive stresses and also the strain. So here is actually denoted by the PC over here, where your force in the compression, and then the stress induced at any section of the metal, also known as a compressive stress, denoted by the sigma. C represent the stress. So there will be increase in the cross-sectional area or decrease in the length of the metal. So this ratio known as a compressive strain. So similar to the tensile test, except that the force is compressive. So we can see from this diagram, the specimen is contracts along the direction of the stress. Okay, and this test is used when a material behavior under the large and permanent strain is desired, or when the material is brittle in tension. That's why we move to the compressive stress and strain. So the compression strength is the amount of the stress necessary to cause the rupture or deformation by the predetermined the percentage. Okay, so the diagram is almost similar in the tensile. So we move to the third. The third part is actually the shear stress and strain. Okay, the shear, which is by define is a force applied so as to cause or tend to adjacent parts of the same body to slide relative to each other in the direction parallel to their plane of the contact. Yeah, this is actually denoted by the shear stress. We call it as a tau. So this is actually the instantaneous applied shear load divided by the original cross-sectional area across which is applied. So denoted by the tau, the force applied by the original cross-sectional area. So F is a load applied parallel to the upper and lower faces, each of which has an area that involved. Okay, this is actually the common of the formula. So for the test performed using the pure shear force, the shear stress tau is computed using this formula commonly, okay, which is the S represent the shear. Okay, and then for the strain, we call it as a shear strain, we denoted by this gamma, okay. So this is actually the shear stress can cause one object to slide over another. So if you can see from the animated picture over here, and this is a schematic, represent that the lattice edge of the atom is shifted by the time that giving the force, the external forces. So the formula to calculate is actually is represented by the tan theta, which is the distance of the x divided by the distance of the y-axis. So the shear strain, the tangent of the shear angle that results from the applied shear load, which is the gamma equal to the tan theta, and it is in the percentage. We would call as a theta as a strain angle. Now we move to the fourth, the torsion, shear, and also the strain. The torsion, stress, also the strain. So the torsion is actually the twisting force, T, denoted by the T, that causes the shear stress on the section. So the applied torque, denoted by T, to the specimen and resulting deformation, which we call it as the angle of the twist, are measured during the torsion test. Okay, so the measurements are connected to the shear, which is denoted with the tau, and the shear strain by the torsion formula. So this is actually the torsional tests are normally performed on the cylindrical solid shaft or can be as a tube. So if you can see from this diagram, a shear stress denoted by the tau is a function of the applied of the torque, whereas the shear strain is actually related to the angle of the twist, denoted by the tau, denoted by the angle here. Okay, so here what you can see, the torsional forces produce a rotational motion about the longitudinal axis of the one end of the member relatively to the another member. Okay, so this is actually the common formula that we use in order to calculate the torsion. So many structurers experience torque, which is the torque range, car shaft, etc. And therefore, it is very important to quantify the stress caused by the torque to help us design the safe structure. So you can see here the concepts of the stress and strain, which is the common state, where actually the principle of the stress and strain used in our daily routine. So this is a simple tension example. The cable we use here in order to pull here the belt, and the torsion, a form of shear, as a drive shaft, is a combination between the two types of the stress and also the strain. Another one example here where you can see the concept of stress. You can see where that in this case it is a compressive structure member, yeah, where this kind of the rock, yeah, is been pushing down onto the another one rod to be supported, yeah. And also can be similar concept where the bridge being supported by the slab. Right, now we do the example 1 to recap back the concept of the stress and strain. So the elongation elastic computation. So the question given, a piece of copper originally 305 millimeters long is pulled in tension with a stress of a 276 megapascal. If the deformation is entirely elastic, so what will be the resultant of the elongation? So in this case, they give you the value of the modulus of elasticity as well as the shear modulus and the Poisson ratio. Okay. So the solution is, since the deformation is elastic, so we can calculate the strain is dependent on the stress, yeah, according to the standard of the equations. Yeah. So we know that the elongation is related to the original length, the L naught, through the equation 6.2, which is this is from the textbook Callister. And combining these two equations and solving the changes in length can actually yield the stress equal to the epsilon is the strain, and this is actually the modulus. As the original formula modulus is E equal to the stress over E. This is under the Hooke's law. So you can substitute here the changes of the strain into this formula, and you rearrange back the formula, and you substitute the value of the 276 megapascal and 305 millimeter respectively. And you can get the value of the modulus of copper from the table that we given in earlier. And then you can substitute the value, all the value, and solve the question. Yeah, 276 megapascal, 305 millimeters, yeah, divided by the modulus. Then you will obtain the changes of the length 0.77 millimeter. Okay. So another example where that 85 kg woman stands on the vinyl floor wearing a stiletto high heel shoes. So if the heel has the dimensions shown, determine the stress she exerts on the floor and compare it with the average normal stress developed when the man having the same weight is wearing the flat heel shoes. So you need to assume the load is applied slowly so that the dynamic effect can be ignored. Also assume the entire weight is supported by the heel of one shoes only. Okay, so this is dimension being given here. Remember that the formula, the sigma equal to the F over the A. So the dimension given in order for you to calculate the area. Okay, the question asks you to calculate the stress, which is the sigma. The force that given over here is actually the weight, where that you need to change it into the Newton units. Okay, right? So now we look at the solution, whereby that you calculate the area, yeah, and then you substitute the value onto the formula that you know the sigma equal to the F or P over the A. And substitute the value. We know that the weight of the person is actually 85 kg. In order to convert to Newton, you need to times with the gravity, 9.81 Newton. So you will obtain, in this case, you multiply with the 9.81 Newton divided by the 125.86 from the area that you already calculated. Then you will obtain your stress at the moment. You will get your stress at the 6.62 M. And then calculate also for the unit is wrong. So calculate for the flat heel shoes as well. So substitute the value, you will get these answers. So it's more likely directly from the values substituted the formula. Okay. So we end our part 1, the concept of the stress.